talking a little bit about what we're seeing in the environment, both in terms of global ocean acidification trends as well as more regional ones. Chris.
Thank you, Sarah. Yeah, I'll start globally with sort of Ocean Acidification 101 with the forcing functions. And then I'll start talking about some of the work in the Florida Keys and show some data that backs up what Mike Crosby said in his introduction. We thought that OA might be a problem for the future, but I'll show you some data that suggests that it's much more imminent in our area. So I want to talk about the established science of ocean acidification. This, what I'm showing right now, is the famous Keeling curve. This is really what started the field of ocean acidification, was this data set, which is showing the CO2 concentration in our atmosphere. And this particular observation is made on the island of Hawaii, but now there's a global network of observing stations collecting flask samples of air and analyzing them at labs around the country, or around the world. And they're all showing this almost exponential increase of CO2 in our atmosphere. Starting in 1960, each year the CO2 concentration is approximately 2 ppm units higher than it was the year before, and it's incredibly consistent. The wiggles you see here are seasonal variability. So the Earth's biosphere, as things photosynthesize and then respire, are causing this seasonal variability. But superimposed on this is the buildup of CO2 produced by the burning of fossil fuels and cement production and the burning of the world's forests. I like this curve. This puts together the instrumental record that only began in 1960 with the ice core record that goes back now 800,000 years, or almost 1 million years, from the Earth's up in Greenland and Antarctica ice record traps bubbles of the atmosphere, and they can be analyzed, and you can measure the compensation or concentration of CO2 in our atmosphere going back almost 1 million years. And the wiggles you see in this figure are the glacial interglacial cycles of Earth's climate. And I show it to show just how abruptly the CO2 concentration has begun to change. It's just almost a straight edge plot going straight up. The blue dot there said in 2008 is the concentration, average annual concentration in 2008. The green dot and the yellow dots are showing 2 projections of where it could be by the end of this century. So all of our life forms on Earth are used to CO2 concentrations in the range of 200 and 300 ppm over the last 1 million years. And then with the beginning of the Industrial Revolution, we're doing a grand experiment changing the CO2 concentration in the atmosphere at an incredibly rapid rate. So not only are the concentrations completely outside the envelope of what organisms have seen for the last 1 million years, what we think may be more stressful is the rate of change. We know that organisms have a tremendous ability to adapt and acclimate, but we don't know how quickly they can do that. And here we're asking them to do that within 100 years in order for them to survive. And we all hope that they can, and it'd be hard to get up each day if we didn't think they could. But it's an unknown question. It's an experiment that we're performing on the Earth's life support system, actually, if you want to look at it that way. So this figure, I'm combining this, that was atmospheric data. Now I'm combining atmospheric data. The Keeling curve is repeated in red with ocean chemistry data. So in particular, in the blue, I'm showing the CO2 concentrations measured in the water at a time series station that was begun in 1989 off the big island of Oahu. So you can see that since that data started being collected, that it's been tracking the atmosphere. It's always less in the atmosphere because the CO2 is getting into the water by diffusion from the air above it. But each year, it's going up by the same amount as it is in the atmosphere. So the atmosphere is forcing changes in the chemistry of the ocean underneath it. And again, you see a lot of wiggles from year to year. And within the season, that's the biological activity that can act and actually change the pH, increasing it during the summer, decreasing it during the winter. But in the long term, it's increasing as forced by the changes in the atmosphere. And then shown in green are the pH of the water. So CO2 is an acidic gas, and as it dissolves into the water, it actually lowers the pH of the water. Now, the pH of the ocean is on average, is slightly alkaline. Remember, on the pH scale, neutral is 7.0. Anything above that is alkaline. But the direction of the change each year is downward, and that's why we call it acidification. The same as if the climate was warming, it's the direction of the change that we're talking about. So this is what I talk about when I say the established science. No scientist anywhere is going to argue these facts. So now I want to bring it locally. This is a map of the Florida Keys. And pictured here is a CO2 ocean acidification monitoring buoy. There's a few of these around the world. This is the only one in the continental, just the only one in Florida. And it's located off the southern tip of Isla Morada at a coral reef named Chica Rocks. It was placed there in December of 2011, and it's been collecting data ever since. Every 3 hours, it collects a measurement of the CO2 concentration in the atmosphere and in the water, and additional parameters, environmental parameters as well. This is what that data set looks like. So here it's measuring in the dark blue the CO2 concentration of the water over 3 years. And in the light blue, along the 400 ppm line, are the measurements of the CO2 concentration in the atmosphere. Now, over 3 years, you can't see the increases that we're talking about on the other figure. That's only more apparent when you look at longer time scales. But what's of interest is the variability that we're seeing at this particular reef in the Florida Keys. And you'll notice that there's an annual cycle in it. It tends to go down during the summer, and we think that's due to the photosynthesis of the extensive seagrass beds that we find out there. So as plants photosynthesize, they remove CO2 from the water, and they'll lower it lower than the concentration in the atmosphere. But then during the winter, the seagrass tend to die off, and they're broken down by bacteria, and the CO2 that they remove during the summer is released back into the water. So the annual average of the concentration of CO2 in the water is very close to that in the air above it. What I wanted to point out now is, seeing these red circles here, is that the CO2 levels tend to get quite high during the winter months of each year. So what I'm showing you here now is monthly measurements of the calcification rate of the reef at Chica Rock. And you can see, and the heavy black line is the annual average, which is positive. This reef is still producing calcium carbonate and fairly healthy. But you'll see that during the winter months, it actually swings negative, and it's actually starting to dissolve. And this is exactly the time when the CO2 concentrations in the water are at their highest, and the pH of the water would be its lowest. And we know that the physiological effect of this is to cause corals to calcify more slowly, and it also activates the activity of the boring sponges that Shirley was talking about. So this allows us to see what the net balance of these two effects are on the annual cycle. Also, as a part of my research, this was an NSF funded study to look at how this is affecting the coral health over the entire Florida reef tract over 2 years, 2009 and 2010. And what I'm showing you here are 7 reefs, starting to the north at Fowey and going down to Lou Reef in the south. And then the bars are showing you the calcification rates of the reef in the summer months, and then in the darker bars during the winter months. And you can see that there's a trend, and as you start the north near Fowey, dissolution rates are actually dominated on an annual basis. It still produces some during the summer, but during the winter, there's really extensive dissolution rates. Now, we had not expected to see this. This is a bit of a surprise. The projections were that this wouldn't start happening for another 30 or 40 years, to like 2050 or 2060. But here's evidence that it's happening in the Florida Keys today. It's more of a seasonal effect now, but it could become annual in years to come. And it appears to be a problem more in the northern part of the reef tract. As we move further south and you get to the 7 Mile and Lou Reef area, they're still calcifying year-round. Slower in the winter, but still healthy and still producing. And this makes a lot of sense to people that know the reefs and get out and visit them. These trends make sense. So as I said, these are surprising, and the findings are that the reefs are already starting to dissolve, even if for only part of the year. But it's a surprising and alarming trend that we didn't expect to see this soon. And we only know it because we're getting out there and making the critical measurements that needs to be done. And obviously we need more of these measurements, and we need to hit more areas. The good news is that some of the reefs are still in pretty good shape, and if we start to doing things and cutting CO2 emissions, things can probably rebound. But it's getting later and later to start to do anything. So I just wanted to finish with this slide. There'll be more talks about the economic consequences of this. But the things that we're seeing on the reef can have real consequences to the economy of South Florida. Estimates are that it brings in about $6 billion a year into the state's economy. And it's in various ways. I mean, people are coming down to fish and to scuba dive, but they're all buying fuel, they're buying bait, they're staying at hotels, buying restaurant meals while they're here. So all these tremendous knock-on effects that a lot of industries and jobs can be impacted if these reefs aren't healthy. Thank you.
Thank you, Chris. The next speaker we will have will be Kim Yates from the U.S. Geological Survey. And this is her presentation. And she will be talking a little bit about the regional context of ocean acidification that USGS has been looking at in Florida. Yeah, take it away.
Thanks, Sarah. So we've heard a lot about some of the biological and ecological impacts of ocean acidification, and Chris provided a nice overview of some of the physical consequences of ocean acidification and carbonate dissolution. And this provides a nice lead-in to discussing ocean acidification from the regional context of Florida. This is important because Florida has some issues that are rather unique relative to other regions of the U.S. And this will provide a segue into our next panel discussion about regional resource management in Florida. I am from the U.S. Geological Survey, and so you have to have a little bit of a geological lesson for ocean acidification as well. So Florida is a carbonate platform that developed several million years ago when sea level was much higher, and most of the Florida Peninsula was underwater as a shallow tropical sea. During that period of time, calcifying organisms produced carbonate, which accreted into the carbonate platform that extends out along our coastal shelf. Over time, changes in sea level alternately submerged and exposed the carbonate platform, creating what we call karst topography. And if you look at the photographs on your right-hand side, you can see that this karst topography is caused when sea level is low and the carbonate bedrock is exposed to fresh water, which dissolves carbonate material, and also weathering. And this creates what we call sort of a Swiss cheese structure in the carbonate material that looks like solution holes. And so you can see we have a mantle of sediment in Florida today that overlies this carbonate bedrock that's essentially full of holes and looks like Swiss cheese. This karst topography forms Florida's sinkholes and aquifers. Sinkholes are formed by a process that looks very similar to ocean acidification. Basically, you have carbon dioxide combining with water in the atmosphere, and that water percolates down through that overlying sediment mantle where it can dissolve the underlying carbonate bedrock. And over time, as that structure becomes compromised, that causes depressions and sinkholes to form. And so you can see how increases in atmospheric carbon dioxide might exacerbate this process. Our Florida aquifer system is also lies within this karst topography, and especially our Upper Floridan aquifer. The Upper Floridan aquifer holds most of the groundwater that we extract in Florida and is also the source of most of our springs. One of the issues that we worry about in Florida is that this karst topography develops what we call leaky coastal margins. And this is why we have so much transport of groundwater from the land to the ocean and also saltwater intrusion. And so we have to worry a little bit more in Florida about land-sea interactions with respect to ocean acidification. Also, our coastlines and coral reefs are supported by this carbonate platform. This is a cross-section of the Florida Keys carbonate platform. You can see the underlying bedrock is nearly exposed in many places in the Keys. And in fact, the bedrock is exposed along most of the shorelines of the Keys themselves. There's a picture on your left-hand side that shows that that bedrock comes up to the surface along many areas in the Keys, and it provides protection from coastal erosion and storm and wave impacts. Our coral reefs grow modern coral reefs grow right on top of this bedrock as well. And this is a particular concern as we know our coral reefs are in a state of decline. And these reefs also provide protection from storm surge and waves. And so in a place like the Florida Keys, when most of your real estate is only 1 to 2 meters above sea level, we begin to worry about loss of these kinds of structures. So the environmental setting is really important because the underlying geologic setting can be a primary control on ecosystem function. We know that ocean acidification can cause dissolution of carbonates, and both ocean acidification and carbonate dissolution change seawater chemistry, and this can cause a variety of biological and biogeochemical feedbacks. So this gives us more questions to consider from the broader regional context. First of all, how will ocean acidification affect and be affected by the carbonate structure of Florida? Will there be impacts to aquifers and drinking water supplies? And will there be more transport of fresh water and salt water across that land-sea interface? How will chemical erosion affect our sinkholes, coastlines, and coral reefs? And how might these structural and chemical changes impact the biology and ecology of Florida's both terrestrial and marine ecosystems? We don't have to start from ground one in trying to answer some of these questions. There's actually a wealth of historical information available from a number of different state, regional, and local water quality and ecology monitoring programs that have gone on for several decades. These are examples of just a couple of those that I've pulled out. For example, the Florida Department of Agriculture and Consumer Services has been monitoring water quality at shellfish beds across the state since the early 1980s. The Southwest Florida Water Management District has done both surface water and groundwater monitoring consistently since about the 1990s. And the Environmental Protection Commission of Hillsborough County has over 40 years of water quality data from over 200 stations around Tampa Bay. Now, most of these water quality programs do not collect carbonate system parameters, but have at least measured pH and other basic water quality parameters. So we can synthesize those data and use that as a gauge or a baseline to set the stage for how ocean acidification may impact our Florida waters. These are examples from results of those kinds of syntheses. Lisa Robbins from the USGS synthesized the Florida Department of Agriculture data and showed that pH is decreasing at most of the sites along the coastline of Florida since about the early 1980s. Kira Barrera, who is here today, actually presenting a slide from her thesis, she was one of our USGS interns from USF. She measured spring water pH from 5 of our major springs since the early 1990s and showed that spring water pH has also been decreasing during this period of time. So this is further evidence that ocean acidification is already affecting our state and not a problem that we look forward to in the next 40 to 50 years. It's already here. The bottom slide is actually some work that Ed Sherwood, who is also here today, and I think we'll talk about this later, has done synthesizing 40-year pH data from the Environmental Protection Commission of Hillsborough County since about 1970, showing that pH is actually increasing in Tampa Bay, and this may be in response to recovery of seagrass beds there. And so it's not all doom and gloom around the entire state. So the bottom line is these are very valuable data. These are the kinds of